A billion years had passed since the first stars ignited, and the universe was transformed. The primitive proto-galaxies of the early cosmos had evolved into more structured entities. Spiral arms began to form in some, rotating majestically around bright central bulges. Others collapsed into elegant elliptical shapes, vast collections of stars moving in random orbits around a common center. The chaotic violence of early galaxy formation gave way to more ordered systems, though spectacular collisions and mergers remained common. These galaxies weren't distributed randomly across space. They followed the underlying dark matter web, forming clusters and groups along its filaments. The largest intersections of dark matter strands became massive galaxy clusters, cosmic metropolises containing thousands of galaxies bound together by gravity. These clusters themselves formed even larger structures, superclusters that stretched across hundreds of millions of light years. At the hearts of many galaxies, the small black holes formed from the deaths of first-generation stars had grown enormously. By consuming vast quantities of gas and merging with other black holes, some had become supermassive monsters with masses millions or billions of times that of our Sun. When material fell toward these cosmic leviathans, it formed spinning accretion disks that heated to millions of degrees, emitting prodigious amounts of radiation across the electromagnetic spectrum. The most spectacular of these active galactic nuclei were quasars, the most luminous sustained energy sources in the universe. With the power of trillions of suns concentrated in a region smaller than our solar system, these cosmic beacons could outshine entire galaxies. Some quasars produced enormous jets of particles and energy, extending thousands of light years into intergalactic space, influencing their surroundings on truly cosmic scales. Throughout the maturing galaxies, the cosmic alchemy initiated by the first stars continued at an accelerated pace. Each new generation of stars formed from gas clouds, progressively richer in heavy elements, creating a cosmic chemical evolution. Carbon, oxygen, silicon, iron, the building blocks of rocky worlds, became increasingly abundant. More exotic elements, gold, uranium, platinum, synthesized primarily in supernova explosions and neutron star collisions, and gradually accumulate in the interstellar medium. This chemical evolution didn't proceed at the same rate everywhere. In the dense central regions of galaxies, where star formation was most rapid, the enrichment process moved quickly. In the sparse outer regions, it progressed more slowly. Some small galaxies, forming in isolation from less heavily enriched portions of the cosmic web, remained relatively pristine for billions of years. Within this increasingly complex cosmic ecosystem, approximately 9.2 billion years after the Big Bang, a relatively unremarkable cloud of gas and dust began to collapse within a spiral arm of a mature galaxy we now call the Milky Way. This cloud, enriched by the remnants of countless previous stellar generations, contained all the elements necessary to form not just stars, but a complex planetary system. At the center of this collapsing cloud, a protostar formed, the embryonic Sun. Surrounding it, a rotating disk of gas and dust flattened and cooled. Within this protoplanetary disk, tiny solid particles began to stick together through electrostatic forces, forming pebbles, then boulders, then planetary embryos. The process of planet formation had begun. In the inner regions of the disk, where temperatures were highest, only materials with high melting points could remain solid. Metals and silicates, the building blocks of rock, dominated these regions. From these materials, the terrestrial planets would form. Mercury, Venus, Earth, Mars, each accumulated material from a specific region of the disk, giving each a unique composition and character. The process was violent and chaotic. Planetesimals, bodies ranging from kilometers to hundreds of kilometers across, collided relentlessly. Some shattered into fragments that would later be incorporated into other bodies. Others merged to form larger protoplanets. Each impact released enormous energy, heating these growing worlds from within and without. In the outer regions of the disk, beyond what we now call the frost line, Temperatures were low enough for water, ammonia, and methane to freeze solid. These ice-rich planetesimals grew quickly, forming the cores of the giant planets, Jupiter, Saturn, Uranus, and Neptune. Once these cores reached a critical mass, about 10 times that of Earth, they began to capture hydrogen and helium gas directly from the disk, growing rapidly into the gas giants we know today. Jupiter, the largest, became so massive that its gravitational influence shaped the entire solar system. Its powerful gravity ejected some, forming planetesimals from the solar system entirely. It tugged on others, elongating their orbits or sending them on collision courses with the inner planets. And it prevented a planet from forming in what is now the asteroid belt, a region populated instead by countless rocky and metallic fragments, the leftover building blocks that never united into a larger world. The early solar system was a shooting gallery. For hundreds of millions of years after the planets formed, leftover planetesimals continued to strike their surfaces in what astronomers call the late heavy bombardment. The terrestrial planets, including Earth, were repeatedly hit by massive impactors. One such collision, between the proto-Earth and a Mars-sized body called Theia, ejected enough material to form our Moon, a critical factor in Earth's subsequent evolution. These impacts delivered more than just destructive energy. They brought water, organic compounds, and volatile elements to the inner planets. Earth received enormous quantities of water this way, much of which would eventually form the oceans. Carbon, nitrogen, and other biologically important elements arrived aboard these cosmic messengers, setting the stage for the eventual emergence of life. As the frequency of impacts diminished, Earth began to transform from a homogeneous ball of molten rock into a structured planet. Heavier elements, primarily iron and nickel, sank toward the center, forming a metallic core. Lighter silicates rose toward the surface, eventually cooling to form a thin crust floating on the still molten mantle. This process, called differentiation, gave Earth its layered structure. The formation of Earth's core had profound consequences. As it cooled, the liquid outer core began to circulate through convection, creating electrical currents that generated a magnetic field extending far into space. This magnetosphere would become crucial for life, shielding the planet from harmful cosmic radiation and preventing the solar wind from stripping away the atmosphere. Earth's early atmosphere bore no resemblance to the air we breathe today. It formed primarily through volcanic outgassing, the release of gases that had been trapped within the planet's interior. Carbon dioxide, water vapor, nitrogen, and sulfur compounds dominated this primordial air. Notably absent was free oxygen, which would appear only much later as a product of biological activity. As the planet slowly cooled, water vapor in the atmosphere began to condense. Rain fell in torrents that lasted millennia, gradually filling the lowest-lying areas of the crust. The first oceans formed, acidic, mineral-rich, and hot, but growing and connecting into the global water system that would eventually cover more than 70% of the planet's surface. The interaction between these new oceans and the exposed rocks of the crust initiated chemical processes that would continue for billions of years. Minerals dissolved into the waters, making the early oceans rich with dissolved compounds. Carbon dioxide from the atmosphere dissolved into the waters, making them acidic. These chemical soup oceans would later become the cradles of life. On land, the first continents began to form. Unlike the ocean crust, which was dense and thin, continental crust was lighter and thicker, allowing it to float higher on the mantle below. These primordial continents were nothing like the landmasses we know today, devoid of soil and vegetation, constantly reshaped by eruptions and impacts. They were alien landscapes of bare rock under a toxic sky. Beneath the surface, the mantle churned with convective currents driven by heat from the core and from radioactive decay within Earth itself. These currents created stresses in the cooling crust, eventually breaking it into distinct plates. The era of plate tectonics had begun, a planetary process unique among the known worlds of our solar system, and one that would profoundly influence Earth's development. Where plates pulled apart, new crust formed as magma welled up from below. Where they pushed together, mountains rose or one plate dove beneath another in subduction zones, recycling crustal material back into the mantle. This constant recycling of Earth's outer layer would help regulate the planet's temperature and atmospheric composition over geological timescales, creating a remarkably stable environment despite the dynamic processes at work. Within the mineral-rich waters of the early oceans, particularly around hydrothermal vents where hot, chemical-laden water rose from beneath the seafloor, complex chemistry was unfolding. Simple compounds, methane, ammonia, water, and hydrogen sulfide, reacted to form more complex organic molecules. Amino acids, the building blocks of proteins, appeared. Nucleotides, which would later combine to form DNA and RNA, began to assemble. Energy for these reactions came from multiple sources: ultraviolet radiation from the sun, electrical discharges in the atmosphere, heat from hydrothermal systems, and impact events. Each provided the activation energy needed to create and break chemical bonds, gradually increasing the complexity of the compounds floating in Earth's primordial seas. Over millions of years, these organic compounds became increasingly organized. Lipid molecules spontaneously formed membranes, creating tiny vesicles that could contain other compounds, the first step toward cellular structure. RNA molecules, capable of both storing information and catalyzing chemical reactions, may have formed self-replicating systems within these primitive compartments. The boundary between non-living chemistry and living biology is not sharp, but represents a gradient of increasing complexity and organization. At some point along this gradient, approximately 3.8 billion years ago, the first entities that could meaningfully be called alive appeared on Earth. These first organisms were nothing like modern cells, far simpler, lacking many of the sophisticated mechanisms we associate with life today, but they possessed the fundamental properties of reproduction and metabolism that define all living things. This momentous transition, from complex chemistry to primitive life, represents one of the greatest mysteries in science. The details remain elusive, the exact mechanisms still debated, but the consequences were profound and irreversible. For the first time in our planet's history, entities existed that could harvest energy from their environment, reproduce with variation, and evolve through natural selection. Life had begun on Earth, the culmination of a cosmic journey that stretched back to the first moments after the Big Bang. The hydrogen atoms in Earth's oceans had formed in the aftermath of creation itself. The carbon, nitrogen, and oxygen atoms essential to biology had been forged in the hearts of long-dead stars. The heavier elements had been scattered through space in supernova explosions or neutron star collisions. All had been gathered together by gravity to form our solar system and our planet. From quantum fluctuations in the earliest moments of the universe to the first stirrings of life on Earth, our story has traced an unbroken chain of cause and effect across nearly 10 billion years. We have witnessed the formation of atoms, stars, and galaxies, the creation of elements, the birth of our solar system and our planet. And now, with the emergence of life, a new chapter in cosmic evolution had begun, one that would transform Earth and eventually lead to beings capable of contemplating their own origins. But the story of life on Earth, from single-celled organisms to complex multicellular creatures, from sea to land, from instinct to consciousness, is a vast epic in its own right. The 3-billion-year journey from the first primitive cells to the emergence of humans, beings capable of looking up at the stars and asking where they came from, will be the subject of our continuing exploration of Earth's astonishing history. For now, we leave Earth in its infancy, a young planet with young life, at the beginning of a biological and geological odyssey that continues to this day. The cosmic architects, gravity, nuclear forces, electromagnetism, had completed their initial work. The living architects, evolution, selection, adaptation, were just beginning theirs. Together, they would sculpt our world and everything in it, including, eventually, us. The story of before Earth has now reached Earth itself. But in many ways, the most extraordinary chapters are yet to come. If you enjoyed this episode, make sure to hit that subscribe button and turn on the notification bell so you don't miss the next episode. Also, leave a comment with at least 8 words. Your feedback helps us grow the channel and create even better content for you. Thanks for watching, and we'll see you in the next episode.